All right, functions. For functions, the definition of a function is for every input, there's only one output. In other words, in terms of x and y's, for every x, there's only one y. For every input, there's only one output. That's the definition of a function, okay? The domain is the set of all inputs. The range is a set of all outputs. So the domain is all the x values. Y, set of all y's will be our range, right? All right, so let's go ahead and determine if this is a function or not. I like to also do this as a mapping with my x's and y's. So notice that the x is 1, the y is 2. So the 1 maps it onto 2. 3 maps onto 7. 2 maps onto 9. And 8 maps onto 11. So for every x, there's got to be one y. And that's how I think about this. So for this x, there's one y. For the next x, there's one y. For the next x of 2, there's one y9. For the next x, there's one y. So yes, this is a function, because for every x, there's only one y. And then we'll go ahead and name the domain. The domain is the set of all x values. So 1, 3, 2, and 8. So 1, 3, 2, and 8. Ideally, I put that in order, 1, 2, 3, and 8. The range is all the y's, 2, 7, 9, 11. 2, 7, 9, 11. All right, let's go to the next one. Let's do a mapping for it as well. Erase this part here so we have room for the next mapping. X, Y. So I have -3 going to 4. 5 is going to 6. 7 is going to 4. And -2 is going to 3. So the question is, for every x, is there one y? So let's test it. For this x, there's one y. For this next x of 5, there's one y. For the next x, there's only one y. For this x, there's only one y. So this, yes, is a function. Domain, I'd list all my x's. Range, I'd list all my y's. 4, 6, 4. I don't need to list 4 again. And 3. Let's go to the next one. And let's test it to see if it's a function. -2, 4. -2 onto 4. -1 onto 6. 0 onto 3. And -2 also goes to 8. So for this x, I have two y's, not one y, I have two y's. So I instantly say that's not a function. Fails. For every x, there can be only one y. So once you see the x repeated with different y's, that's a problem. You're not going to be a function. Then you just list all your x's. List all your y's. And you're done with that one. Let's do one more. 5 maps onto 3, -2 onto 1. 5 maps onto 3. Again, it's the exact same mapping, so it's the exact same point, so not an issue. And 9 goes on to 10. So for this x, there's one y. For this x, there's one y. For this x, there's one y. So it looks like, yes, this is a function. And I would again list my domain, 5, -2, and 9. 5, -2, 5, and 9, but I don't need to list the 5 twice. The range, all the y's. Don't need to list 3 again. 3, 1, 3, and 10. So 3, 1, and 10. Well, there is a visual test of whether something is a function. And it says, for every x, there's got to be one y. So let me go back to this one that's not a function up here for a second. Let me graph these points, and I'll show you what I mean. We know this one's not a function, but let me graph these points. Negative 2, 4. Negative 2, 4. Negative 1, 6. 0, 3. And negative 2, 8. So what you do is you run a vertical line through everywhere that it is defined, and it can only hit once. So for an x value of 0, I only hit once, I'm okay. For an x value of negative 1, I only hit once, I'm okay. But when I test an x value of negative 2, I hit twice, I hit there. So it fails the vertical line test. In other words, it's not a function. Now this is just for a set of points. You can do it for graphs too. So I run vertical lines through and I'm only hitting one time. See how this is increasing? I'm only hitting one time. So this yes is a function. This one's okay. It can only hit one time. Here though, see how it fails? This is not a function. It hit more than once. So this is called the vertical line test, because for this x value of negative 2, I'm hitting here and I'm hitting here. For that x value, there's more than one y, right? Remember, to be a function, for every x, there can only be one y. Here, I run the vertical line test. I'm only hitting once. This one's okay as well. So yes, function. Now, what about if you have an equation? Well, what you do is you isolate the y, solve for y, and then you can see that for every y, if you have more than one x value or not, or for every x if there's more than one y, sorry. So 3y squared, I'm going to subtract x squared from both sides, equals 7 minus x squared. Subtract x squared from both sides. Divide everybody by 3. So I have y squared. In fact, I'm just going to write it as 7 minus x squared all over 3. And then square root. Now remember, when I square root both sides, I have a plus or a minus. So think about this. Let's say I plugged in 0 for x. Well, then y would be plus or minus 7 minus 0 squared all over 3, plus or minus the square root of 7/3. In other words, when x is 0, I have square root of 7/3, and I have negative square root of 7/3. So it's that 0 is going to two y values. So not a function. So as soon as you see that plus minus on that, as soon as you see the plus minus, not a function. Now you can be even lazier than that. And the giveaway is, lazier meaning you don't even have to solve it. If you see y to an even power, y to even power, then you will not be a function. If y is to an even power, you will not be a function. If y is to an odd power, that's totally fine. So this will be a function on this next one. And I'll show you here. Let's go ahead and subtract x squared on both sides. And now let's take a fifth root. Well, it's a fifth root. So there's no plus minus involved like with even powers. So whatever x you plug in, there's only going to be one y. So this yes is a function. Okay, so that's algebraically how you look at that. All right, let's do a little bit of function notation. I said f of x is a nickname for y. So here we have f of x equals 2x minus 5. F of x equals 2x minus 5. And what this is telling us, when you're finding f of 3, when they say find f of 3, that means find y, or f of x, when x is 3. So it's just telling you input the 3. 2 times 3 minus 5, and see what we get. 6 minus 5 is 1. F of 3 is 1. So our input is 3. Our f of x is 1. Our y value is 1. 3 comma 1 is our point. That's input, function notation. So it's telling us to plug that in. You might be wondering, why do you do that? Why can't we just deal with x's and y's? Well, mathematicians are kind of lazy, not in the sense that they don't want to work, but they're lazy in their notation. They want to be very, very concise in their notation. So like, for example, when you get into calculus, and the function notation is very convenient for when you're taking derivatives and so on. And here, you don't want to say, find the functional value when x is 3. You want to just say, find f of 3. So that's why they do that. It's very sweet and concise. Now let's do this next part. What about, so f of x is 2x minus 5. Solve when f of x equals 7. So if the functional value, if the y is 7, solve for x. Let's add 5 to both sides. So we have 12 equals 2x. Let's divide both sides by 2. So it looks like x ends up being 6. So if the y value is 7, if f of x equals 7, the solution would be the input must be 6 to make that happen. Let's do some more function notation here. We have f of x equals 2x minus 5. And they want f of x plus 3. So let's plug in. Now we're plugging in x plus 3 in for x. So we have 2, but what goes in there? X plus 3 goes in for x. X plus 3. And then we just clean that up. So we got 2x plus 1. How about f of x plus f of 3? Well, f of x is 2x minus 5. So that's f of x. And we're going to find f of x, and then we're going to add it to f of 3. Now, what would f of 3 be? So let's go to the side, find f of 3. Well, let's plug 3 in for x. So we got 6 minus 5 is 1. F of 3 is 1. So f of x is 2x minus 5 plus f of 3. F of 3 is 1. So f of x plus f of 3 is 2x minus 5 plus 1, which is 2x minus 4. That's what f of x plus f of 3 is. It ends up being 2x minus 4. Now, how about f of x plus h? F of x plus h. And this is leading us to the difference quotient, which will help us out quite a bit in calculus. F of x plus h. So now x plus h goes in for x. X plus h is going in for x. So this becomes 2x plus 2h minus 5. That's f of x plus h. How about f of negative x? F of negative x. So now I got 2 times negative x minus 5. So I got negative 2x minus 5. That's what f of negative x is, negative 2x minus 5. And if f of x is 2x minus 5, then if I put a negative in front of that f of x, then I would have to put a negative in front of that 2x minus 5, right? So negative f of x equals negative 2x plus 5. I'm just putting a negative in front of the original function. All right, let's do a few more with this one. We got f of x equaling x minus 4 over 2x minus 3. And let's run through what would f of 5 be. F of 5. So 5 goes in for x. Five minus 4 over 10 minus 3. So f of 5 is 1/7. If f of x equals x minus 4 over 2x minus 3, f of x plus h would be, now the x plus h goes in for the x's. So I'll have 2x plus h minus 4 over, no. It's x minus 4, I'm sorry. X is x plus h. There's the x minus 4 over 2x minus 3. But again, the x is x plus h. So now we just got to clean that up. F of x plus h equals x plus h minus 4 over 2x plus 2h minus 3. And you can stop right there. All right, the next one we'd have f of x plus f of 5. F of x plus f of 5. So f of x is the original x minus 4 over 2x minus 3. F of 5 is now we're punching 5 in for the x's, right? So 5 minus 4 over 2 times 5 minus 3. So this becomes x minus 4 over 2x minus 3 plus 1 over 10 minus 3, 7. If you wanted, you could get a common denominator, or if you're getting a common denominator, you gotta give this 2x minus 3. You give this on a 7. So you'd end up with 7x minus 28 plus 2x minus 3 all over this 7, 2x minus 3. 7x plus 2x is 9x. Negative 28 minus 3 is negative 31 all over 7 times 2x minus 3. That's another form of that. Either of those are correct on that. All right, f of negative x. Well, f of x is x minus 4 over 2x minus 3. F of negative x would be negative x minus 4 over 2 times negative x minus 3. So f of negative x ends up being negative x minus 4 over negative 2x minus 3. I would, this has got so many negatives in it, I would clean that up a little bit. I would take a negative out of the top. I would take a negative out of the bottom. See how the negatives cancel? And so f of negative x is x plus 4 over 2x plus 3. That's a little cleaner answer than the prior one. Well, in this one we got f of negative x, f of x equals x minus 4 over 2x minus 3, and we're finding negative f of x. So it'd be negative the original. So, and you could write it like that. You could also write it like this. You could even distribute it. Any of those. I'd probably stop right there. When you're finding the domain algebraically, what you're looking for is what x values, the domain is a set of all x values. Is there anything I can plug in that will make the function undefined? Right? In other words, is there anything where I divide by 0 or square root of a negative number? Anything like that? Well, in this case, it doesn't matter what I plug in for x, I'll always get a y value. I can plug any real number in for x. So my domain is x such that x is an element of the real numbers. This is element. This is the real numbers. In interval notation, we say negative infinity, positive infinity. X can be anything. And if you think about a line, right, here's that line. Sure, x can be any value. If I plug in negative 10, it'll be on the line. If I plug in negative 1, it'll be on the line. Any x value I pick, it'll be on the line, right? So the x has no restrictions. Let's look at this next one. Y equals 5x squared minus 3. I'm looking, is there anything x cannot be? No, I can plug anything in. So once again, my domain is all real numbers. So I could say that in interval notation, or here it is in set notation. X is an element of the reals. And if you look at this graph, this is a quadratic, by the way. It doesn't matter what you pick for x, it'll have some y value, right? I pick that. Anywhere I pick an x, it'll have a point on the graph. Now this one can be problematic because I have a denominator. Now we know we cannot divide by 0, right? So where am I undefined? Well, anywhere where the denominator is 0. Well, let's solve for x. Let's add 5 to both sides and divide by 2. So I know x cannot be 5 halves. So if I plug 5 halves in, I get it. I'm dividing by 0. So my domain for this, whatever this graph looks like, at 2.5, 5 halves, it'll never touch it. It's broken up there. Again, I don't know exactly what this looks like right now without graphing it, but I do know it never touches that dotted line, 5 halves. So when I do my domain, I say, well, negative infinity up to 5 halves, union, and there's a break. Notice there's a parenthesis on that. In set notation, you'd say x such that x is an element of the reals, except it cannot be 5 halves. Whoops. Do my brackets there. Or my squigglies. I forget what you call those. Now let's look at the next one here. With a square root, remember we can take a square root of 0, that's 0. We can take a square root of 1 or any positive number, right? We cannot do this, not in the real numbers. Can't take the square root of a negative. So when you see a square root, when you're finding the domain, you say, well, that stuff's got to be greater than or equal to 0. Whatever the radicand is must be greater than or equal to 0, and then you solve it. Add 5 to both sides. Divide by 2 on both sides. So x has got to be greater than or equal to 5 halves. So what this one kind of looks like is like that. It's going to take off from 5 halves, and it's going to keep going to the right. In other words, x such that x is greater than or equal to 5 halves in set notation. Okay? All right, this next one has a square root and it has a radical. So first of all, remember I cannot divide by 0. Cannot. So I know if this is 0, I have a problem, right? In other words, if I take the square root of 0, so if 2x minus 5 is 0, I have a problem. If x is 5 halves. If x is 5 halves, I'll have the square root of 0 on the bottom. So I know x cannot be 5 halves. In addition, I have a radical. So 2x minus 5 typically has to be greater than or equal to 0, but we can't have it be equal to 0. So we have to have it be strictly greater than 0, because if we let it be 0, I'll have a 0. I'll be dividing by 0. So in this case, 2x minus 5 is just greater than 0. Add 5 both sides. So x has got to be greater than 5 halves, not equal to, greater than. So the domain is from 5 halves with a parenthesis on, or x such that x is greater than 5 halves. All right, I think this is my last one as far as, oh, I do have a couple more here. About the third root. Well, the third root of 0 is 0, so I cannot divide by 0. So x minus 3 can't be 0. In other words, x can't be 3. If x is 3, I have an issue. And that's my only issue, because I can take a third root of any number, positive or negative. I just can't have it be 0 because I would be dividing by 0. So my domain is negative infinity up to 3, union 3 on. Or x such that x is all reals except for 3, because 3 makes it so I'm dividing by 0. How about this one? Can x squared, I can't divide by 0. Where is that 0? Well, if I solve this, x squared, and I'm like, oh, I can't do that. I can't take a square root of a negative number. X squared is always positive, and then I'm adding 9 to it. This will never be 0. So this domain has no restrictions. Negative infinity, positive infinity. So all reals. All right, how about this one? We have in the denominator, I can't divide by 0, so x can't be 6. And my other restriction, look at my numerator. I have a square root, so this stuff underneath has to be greater than or equal to 0. So x has got to be greater than or equal to 3, and I cannot be 6. X is greater than or equal to 3, but I cannot be 6. Greater than or equal to 3. So I'm going from 3 on, but there's a break at 6. So 3 up to 6, including 3. Do not include 6. And 6 on. All right, the last part is a difference quotient. In calculus, we're going to do this. The usefulness of the difference quotient will help us to find a slope at a point. And so this difference quotient is f of x plus h minus f of x. So here's the point x plus h, f of x plus h. It's just the point there, and this is the point x, f of x. So if you find that slope, you'll have f of x plus h minus f of x, y2 minus y1 over x plus h minus x. So the x's cancel on the bottom, you're just left with h. So we just want to practice this algebraically, is all we care about in here, is can you find the difference quotients with function notation. So f of x plus h. So let's go to the side for a minute. F of x equals 2x minus 3. F of x plus h would be 2x plus h minus 3, which is 2x plus 2h minus 3. So that goes in for f of x plus h. 2x plus 2h minus 3. Now we have minus the original function f of x. Well, the original function is 2x minus 3. So I'm subtracting the original function. Divided all by h on the bottom. And now we just clean this up. 2x plus 2h minus 3 minus 2x plus 3 all over h. Notice my 2x's cancel. My negative 3 plus 3 cancels. So this just becomes 2h over h. And my h's cancel. So this is just left with 2. Let's do it for this one. A little bit more complicated for this one. Here's my difference quotient, f of x plus h minus f of x all over x plus h minus x, which is just an h. Let me go to the side. Here's my f of x. F of x plus h then would be 3x plus h squared minus x plus h plus 1. Let me plug that in right here. 3x plus h squared minus x plus h plus 1 minus the original function, which is 3x squared minus x plus 1, and this is all over my h. Now let's expand this. This is x plus h, another x plus h, minus x minus h plus 1, minus 3x squared plus x minus 1 all over h. Now I'm going to FOIL this, so I'll have 3x squared plus xh plus xh is 2 of those xh's plus h times h is h squared. Minus x minus h plus 1 minus 3x squared plus x minus 1 all over h. Well, let me distribute this, so 3x squared plus 6xh plus 3h squared minus x minus h plus 1 minus 3x squared plus x minus 1 all over h. All right, 3x squared minus 3x squared, that's gone. Looks like I have a negative x plus an x, that's gone. And finally I have a 1 minus a 1, that's gone. So what am I ending up with? I have 6xh plus 3h squared minus h all over the h. Now what I do is I factor an h out of the top. So I have 6x plus 3h minus 1 so that the h's cancel right there. And I'm just left with 6x plus 3h minus 1. This is our answer for the difference quotient. Okay. Let's do one more. Promise this is our last one. We'll call it good here. F of x plus h minus f of x all over h. Well, f of x plus h would be 3 over x plus h minus 1 minus the original function, 3 over x minus 1. And this is all over h. So what I got to do is I got to get a common denominator. Right now, this denominator is x plus h minus 1. This one needs that. And this one over here has an x minus 1 right here. This one needs that, x minus 1. So I've got to get a common denominator first. So I'll have 3x minus 1 minus 3x plus h minus 1. And this is now all over my common denominator. And then this is all over h, or in other words, h over 1. So I have one fraction over one fraction, so I'm going to multiply by the reciprocal. And so what I have is, let me multiply this as well, 3x minus 3 minus 3x minus 3h plus 3 all over common denominator times 1 over h. Well, notice 3x minus 3x, that's gone. Negative 3 plus 3, that's gone. So in my numerator I have negative 3h times 1. My denominator I have x minus 1, x plus h minus 1, and then I have times h, and I'm going to put that h out front. And then hopefully you see those h's will cancel right there. Everything's being multiplied, so it'll cancel. I'm left with this as my final answer to my difference quotient. Thanks so much for watching. See you guys next time.